Question 1. So a car moves along a straight horizontal road. The car starts from rest at a fixed point A on the road and moves with constant acceleration for 30 seconds, reaching a speed of 15 meters per second. Speed is then maintained. When the car has been moving for 15 seconds, a motorbike starts from rest at point A and moves along the same road in the same direction as the car. Motorbike accelerates at a rate of 1.5 meters per second squared so that it catches up with the car when the car has been moving for t seconds. So part A, using the same axis, sketch a speed time graph of the car and the speed time graph of the motorbike up to the time when the motorbike catches up with the car. Okay, so it's a lot to take in. Just read it first and then digest the information. It's asking for a speed time graph, so we can start by drawing the axes for our graph. So we'll have the x-axis will be the time axis, so there we go, and the y-axis would be our speed axis or velocity axis, so that's v. Okay, so let's start with the car. If you look at the question, it says that car starts at rest, so from rest, from a fixed point A. Well, fixed point A would be where t equals 0. So now the time axis, just to mention, because there's two objects here, there's two reference frames here. Well, technically it can be 3 reference frames, but let's say we are following the clock on the car. So the time axis is the time that's ticking on the car. So the clock is actually on the car itself. So the time is relative to the car. So when t is equal to 0, the car starts at rest. So the speed of the car is 0. So this is the point where a car starts from on the graph. It moves with constant acceleration for 30 seconds, reaching a speed of 15. So from here, constant acceleration means the graph will be a straight line. And on the time axis, we need 30 seconds. So let's say 30 seconds roughly there. So if we drop down from here, this would be 30 seconds. And the speed acquired in those 30 seconds is 15 meters per second. Okay. And the acceleration, obviously, we don't have that yet. We're not given that. So all we know is that it's constant acceleration. That explains why this is a straight line. And this speed is maintained. So going forward from that point onwards would be a horizontal line. That speed is maintained. When the car has been moving for 15 seconds, a motorbike starts from rest at point A. Now, if we read this line here, the fact that it starts from point A, one of the common misconceptions is that you would think that, hang on, if it starts from point A, does that mean it starts from the origin? No. It starts starts from 15 seconds. So when time is 15 seconds, that's where it starts from on the time axis. But remember what I said earlier, the time is the car's time point of view. So the clock is on the car. On the clock of the time of the car, it says 15 seconds. That's when the motorbike starts to move. So when time is 15 seconds on the car, that's where the motorbike graph starts from rest. So at this point, the speed is 0. Okay, and it says that the motorbike accelerates at a constant rate of 1.5. So it goes up. Now, if we make that, we can make that parallel, or we make that steeper or less steeper. I mean, because we don't have the acceleration of the car here, I mean, we can work it out, but it doesn't really matter. All we need is the constant acceleration for the motorbike going straight up. Okay, so let's just say it goes up to there. Obviously, we need the motorbike to travel fast enough to catch up with the car. So the graph speed of the motorbike obviously has to be. I mean, it doesn't matter if it's more than 15 or less than 15. It's just a sketch. So I'm not going to put any numbers in. Even if it doesn't fall in the right place, when you do the maths, they will fall in place when we have to work anything out. So let's just put it here. It says that so it starts at 15 seconds from rest, and it moves in the same road, same direction as the car, the acceleration is 1.5. So the gradient of this line, which is acceleration, is 1.5. And it travels for t seconds, capital T seconds. So it catches up with the car when the car has been moving for t seconds. So when the car has been moving for t seconds, so hence the time on the car would be t seconds. So let's say that this is your time t seconds. So that at this time, both the car and the bike have caught up with each other. Well, the bike has caught up with the car because they started from the same point, and they caught up. The bike has caught up with the car at some specific point. What can we say about the distance traveled by the car and the bike from point A to that point where it catches up? Would be the same or different? Would be the same distance. And what gives us the distance in a speed time graph? The area. So yeah. So question A is done. Anything we left out? We don't have the speed of the bike because all we're given is it accelerates for t seconds. Yeah, that's it. Right, so find the speed of the motorbike at the instant when it catches up with the car. Right, so for part B, we know that the distance is covered is the same for both the car and the bike. So if we were to work out the area of the bike, which is this area here, it would be same as the area covered by the car. So area covered by the car. Let me just do it separately here. So let's work out the distance traveled by the bike. Yeah, so distance traveled by the area underneath the curve. So if we look at the graph, it gives us the triangle. Right. So for this triangle, the base of the triangle is t minus 15. The height of the triangle would be the speed that the bike reaches at the moment when it catches up with the car. So let's just say that's v there. So height so far is v. V equals to u plus at. We know that it starts from rest, so 0. Acceleration is 1.5. And the time it was accelerating for, okay, so the time it was accelerating for is the time between 15 and t, capital T. So it would be t minus 15. So our v in that case, if we were to expand this out, well, let's just leave it as 1.5 times by t minus 15 for now. So that's basically the height of the triangle. So the area of the triangle, therefore, is going to be a half times t minus 15 times by the height, which is 1.5 times t minus 15. And if we multiply this out, so 3 over 2 times half is 3 over 4. And if we expand the double brackets, so that's t squared minus 15t minus 15t, that's minus 30t plus 15 squared is 225. And if we multiply the 3 quarters into this equation or expression, we get 3 quarters of t squared minus 3 quarters times 30. So 45 over 2. T plus 675 over 4. So that's the expression for the distance traveled by the motorbike. And then if we work out the distance traveled by the car, it's going to be the same distance. And if we draw the graph for the car, what shape do we get? Yeah, we get a trapezium. So the height of the trapezium is 15. The base of the trapezium from here to here is capital T. And the top bit here, what's this bit? Yeah, so it'd be t minus 30, not 30 minus t. The t is bigger than 30. So the area of trapezium is you add the top and you add the parallel sides together. So t plus t minus 30 divided by 2 times by 15. So that gives you 2t minus 30, divide them both by 2, and times by 15. So that's t times by 15, so that 15t. And then 15 times 15 is the minus 225. Now, given that the distance traveled are equal, right, so this means that 3 over 4 t squared minus 45 over 2t plus 675 over 4 has to equal to 15t minus 225. And if we rearrange that, 3/4 of t squared minus 75 over 2 to t, then 675 divided by 4, add 225. That's 1575 over 4 equals to 0. If we put that into our quadratic formula or the calculator, can we work out the coefficients or the solutions to this quadratic? And the other one is 15. So both of them positive. Well, what happens at t equals 15? We start off at t equals 15, the clock time on the time on the car. So at t equals 15, they start off at that time. The next sum they're together is 35 seconds later. So the answer therefore is 35 seconds. Right, find the speed of the car, of the motorbike, at the instant when it catches up with the car. So now that we have the t value, the speed of the motorbike, if you go back up to this bit here, from this bit, right? So v equals to u plus at. So it's just acceleration is 1.5 times the t value that we have. So speed of the bike is equal to v equals to u plus at. It starts at rest, so 0 plus acceleration was 1.5 times by the time. We should get 52.5 meters per second. It says find the speed of the motorbike at the instant it catches up with the car. And distance, we have the distance. We worked out from the area. Well, we didn't really work out the area. We just equated them. We just equated the areas to find the time. Because to work out the speed, it's v equals to u plus at. We need the time. So the time. Hang on a second. No, I don't think that's correct. T equals 35 is how long the car has been traveling for. The motorbike has been traveling for 35 minus 15 seconds. I think we should have seen that from here. Right? This is the formula to get the speed. It's t minus 15. So v equals to 1.5 times by 20, which is 30 meters per second. Right, question 2. A ladder AB shown in figure 1 has a length of 2a and weight of w. So distance from there to there is 2a. Before I put the weight in, I want to see if that rod or if that ladder is uniform. And usually, if it's not written somewhere above, it will be at the end where the assumptions are. And look at what it says here. So uniform rod implies that the center of mass of the ladder will be at the center. So somewhere here. So this distance will be the same as that distance here. Now weight acts vertically downwards all the time. Okay, so the force acting downwards, is it going to be W or is it going to be WG? It's going to be W, because weight is your force. W equals to mg. If you were given mass, then you'll be mg. But here you're told that weight is W, so in that case it's just W going down. It rests on equilibrium at point A on the rough horizontal ground. So point A is rough, meaning there's going to be friction. So if the floor wasn't rough, which way would our ladder slide towards? Point A will go towards the left, wouldn't it? Imagine when they climb up the ladder, what's going to happen? If its floor was icy, it's going to move towards the left. Therefore, friction must be towards the right. So that's the direction of our friction. Okay. Now, point A of the ladder is pushing down on the ground, so the ground must be pushing back up, and it will be perpendicular to the ground. So this is going to be our reaction A. This is just how I the notation. That's the reaction at A, and that's the friction at point A. The other end B rests along against a smooth vertical wall. So at point B, we don't have any friction because it's smooth, but we definitely have contact. Therefore, we're going to have a normal reaction off the wall, which is perpendicular to the wall. And that's reaction B, which is perpendicular to the wall. Show that mu equals to this. Okay, so the next line here is quite important. The ladder is at its point of slipping. That tells us something about friction. Yeah, it's at the point of slipping, so it's just about to move. The ladder is just about to move. So therefore, friction, would it have to be smaller than its maximum value, or would it be equal to its maximum value? It will be equal to its maximum value. Friction is always less than equal to mu times r. But the fact that it's at the point of slipping implies that friction is at its maximum value, which is mu times r. So maximum. Because it's about to move, it means that it's going to be a maximum value. So if the friction is mu times r, we can rearrange that to make mu the subject. So mu, therefore, is going to equal to the frictional force divided by the reaction at A. So once you work out what your friction is, and then you work out what your reaction is, once you get those expressions, you then divide them, and that gives you mu. And that is basically what we need to show. It's a show question. We need to show how we get the friction, how we get the reaction, divide them, and show that it simplifies into that expression given here. So let's start by looking at the forces we have in the diagram. I think we have annotated all the forces given. Okay, so how many unknown forces, apart from W, how many unknown forces are there? Yeah, which three? And friction. Good. So the red forces and the blue force. So what can we do to eliminate all forces apart from one of those unknown ones? Take moments. Well done. So where do we take moments from? Point A. So if we take moments from point A, because we are in equilibrium, the total moment at point A is going to add up to 0, because equilibrium means there's no rotation. So this means the total clockwise moment is going to equal to the total anti-clockwise moment. Both ways will balance each other off. Now, the fact that the red forces, the reactional force at A and friction, they both originate from point A. So those forces, if we were to take moment from point A, the turning effect of those forces will have a magnitude of 0, because they go through point A. So the distance from point A is 0, therefore no moment from those two forces. So we can literally just ignore those forces now. So the only two forces remain is the weight and the reaction at B. So if we were to pivot from point A, the W is going to turn it clockwise. So clockwise, so I'm just going to make a note that W is going to turn it clockwise. Therefore, the reaction at B is going to turn it anti-clockwise. So let's start with the clockwise one. So W is going to turn it clockwise. The formula for moment is force times the perpendicular distance. So W times the perpendicular distance. Now the distance we want from point A has to be right angles to the force, to the line of action of the force. So is this the distance? No, because it doesn't make a right angle. This angle here is not a right angle. So if we go down, right, is this a right angle? Yeah, good. So this is the distance we want, which is perpendicular to the line of action of the force. That's the distance we want to work out. So this is angle theta. The hypotenuse of the right angle triangle is A, and we want the adjacent. Adjacent is A cos theta. So that's A cos theta would be the horizontal, the adjacent distance. So it'll be W times by A cos theta equals to the anti-clockwise direct force, which is the reaction at B, times the perpendicular distance. Now, the perpendicular distance of RB, from point A to RB, is clearly not this, because that doesn't make a right angle here. So if we were to follow the line of action of the force, right, can you see where it's going to end up? So if we were to follow the line of action of the force of reaction B, and go straight up from point A, this makes, say, right angles with the line of action. But I don't want to draw this here, So, but I'm going to draw it here instead. So that distance here, is it the same as this distance there? Yeah? And that's the opposite to the bigger right angle triangle where the hypotenuse is 2a. So opposite means it's going to be 2a sine theta. So it'll be RB times by 2a sine theta. We can divide both sides by a to cancel off the a's. And if we rearrange that to get w equals to RB times by 2 times sine theta over cos theta. And sine over cos gives us tan. So therefore, reaction at B will be equal to W over 2 tan theta. There we go. We have a reaction at B. Now, the main two forces we want to work out is friction and the reaction at A. Now, to work those out, we're not going to take moments. We're now going to resolve the forces. So we're going to resolve the forces horizontally first. If we resolve it horizontally, what forces are acting horizontally is going to be friction and reaction at B. Those are the forces acting purely horizontally. And there's no other forces acting horizontally. So this means that the friction force has to balance off the reaction at B, which is equal to tan theta. There we go. So we have the friction. It's W over 2 tan theta. If we now resolve the forces vertically, right? So vertically we have the reaction at A, that's vertical, and we have the W, that's vertical, and there's no other forces. So this means the reaction at A therefore has to equal to W. And if we now go back to this section here, we have everything to work out mu now. So mu therefore is going to be the frictional force, that's W over 2 tan theta divided by W, or if we use your keep change flip, so times by W over 1 flips into 1 over W, and what happens with the W's? They cancel out, so mu is therefore 1 over tan theta, which is basically what we needed to show. If the ladder were not modeled as uniform, state how this would affect the calculated value of mu. Explain your answer carefully. Right, so if the ladder was not uniform, it will affect the position of the center of mass, correct? The center of mass could be higher or it could be lower down. Regardless of where it is on our ladder, the size of the W won't change. So if it moves lower down if we take moments from point A, if it moves lower down, the distance will reduce from point A. If that reduces, the turning effect of W will go down. If the turning effect of W goes down, the turning effect of RB will go down. And if RB goes down, then RB is what friction is. Friction will go down. W hasn't changed. W won't change. The reaction A will stay the same. Okay, so if the center of mass is closer to point A, so if the center of mass is closer to point A, the moment of W will decrease, and as an effect, the reaction at B will decrease, and as an effect, the friction will decrease. But the reaction at A will not change. That will still be W, will not change. And if you look at how we work out the mu, it's equal to the mu is equal to friction divided by reaction. If the denominator doesn't change, but the top changes, the reaction at A stays as W, but the friction decreases. If the friction decreases and reaction A doesn't change, what would happen to mu? It will go down. So this implies that mu will decrease. So if the center of mass is lower down, friction will reduce. If the center of mass is higher up, it will go up, it will increase. There you go. Because if the center of mass goes up, the moment will increase, so everything else, the friction will increase, and vice versa. All right, so question 3. A particle moves under the action of a single force F At time t seconds, the position vector of r is given as, I prefer to write in column form, so that's t cubed minus 5t, and j is 5t squared plus 6t. Right, so the mass is 0.5 kilograms. At time t seconds, p is moving in the direction with that vector. So when t equals t, we're not given the magnitude. We're given the direction. It's moving along. It's moving in the direction given by the vector of I plus 2j. So the three vectors we have the position vector, we have the velocity vector, and we have the acceleration vector. So when I said which one gives the direction, I meant out of those three, which one gives you the direction of motion? Is it the position vector, is it the velocity vector, or is it the acceleration vector? The direction of motion is given by the velocity vector. Because you're moving in that direction, it means that the velocity vector has to be parallel to this vector. The parallel means same gradient. If two vectors are parallel, it means that they're multiples of a constant multiple of another vector. So v therefore has to be, let's use k as a constant, it will be k times the vector is parallel to, which is 1, 1, 2. So I plus 2j in column form is 1, 2. So find the value of t. Well, first of all, we need to know how to get from position into velocity. So how do we go from r into v? Differentiate. Okay, so we're going to differentiate r to get to v. So dr by dt. So if we differentiate that, so differentiate the top will give us 3t squared minus 5. Differentiate the bottom part gives you 10t plus 6. Right? So this is our velocity vector. We want this to be parallel to k times 1, 2. How many components do we have? 2. So that it will give you two equations. If we equate the x component, the I direction, do we get 3t squared minus 5 equals to 1 times k is? Okay. And if we equate the y component, we get 10t plus 6 equals to 2k. Two unknowns, two equations, simultaneous equation. So we can just substitute in for the k. So if we substitute this k into this the one underneath, we can replace this k with that quadratic and times by 2. So this means 10t plus 6 equals to 2 times k, 2 times everything above. So that's 6t squared minus 10. So rearrange as 6t squared minus 10t, and then minus 10 minus 6 is minus 16. You can simplify or just put into our calculators what do we get the t values. So here it will give you the capital T values. Okay, I guess we're going to ignore the minus 1 because our t value has to be more positive. So cross this out. So t is this. Find the magnitude of F, force, when t equals 2. So what is F equals to? Force equals to mass times the acceleration. So the vector force equals to mass. What was the mass given as? Was it 0.5? Yeah. An acceleration. Right? How do we get acceleration? Good. We differentiate again. So the differentiation of v with respect to t. So if we differentiate v, this was our v. So if we differentiate that, that's 6t, and the bottom would be just 10. But we want to find the acceleration when t equals to 2. So substitute in t equals to 2. So the acceleration is 12, 10. So if we now put it into our force, mass is 0.5, acceleration is 12, 10, which simplifies to 6, 5. We want the magnitude of the force. So the magnitude of F therefore would be the magnitude of 6, 5. So Pythagoras, 6 squared plus 5 squared, square root. And what do we get? Root 61. And Newton's force. Question 4, projectile motion. Right, so the initial velocity is equal to 9, 12. projected with that speed. The ball passes over point A, where h meters vertically above point O, as shown in figure 2. The velocity of the ball at the instant when it passes through point A, so at this point, v equals to constant lambda times by 1 minus 1, which means the same as lambda and minus lambda. So that's the velocity at point A. A ball is moved as a particle moving freely under gravity. Find the value of h. Okay, so to find what the height is, or the time it takes to travel vertically to that height, would be the same as the time it takes to travel horizontally. But we're not given any displacement, so I'm not going to use any displacement equation because we don't have any distances given. We have the initial speed and we have the final speed. From what we can see is because there's no air resistance horizontally, we know that the speed along the horizontal doesn't change. So for question A, if you think of this as ux and uy, and at the end is vx and vy, what can you say about ux and vx when you're moving horizontally? Does the speed change when you're moving? As the particle moves from here to there, it has a speed along the x direction as well as the y direction. The horizontal speed as it moves from one point to the other point, does that stay the same or does that change? Okay, why does it stay the same? Acceleration is 0. F equals ma. Because the resultant force is 0 horizontally, acceleration will be 0. That means it's moving at constant speed. So this means that horizontally, acceleration is 0. So that means ux is the same as vx. So therefore, 9 must be the same as lambda. So we have lambda in that case. Now if you got lambda, we have the velocity in that case at point A would be 9 minus 9. If we now apply suvat in the vertical direction, so S U V A T. So in the vertical direction, S is H, U and V. We're going to work out the magnitudes. A is minus G. So U equals to 9, 12. So can we work out what the speed is? 9 squared plus 12 squared. Is that 15? V equals to 9 minus 9. So the modulus would be 9 squared plus 9 squared, 9 root 2. So that's 15, 9 root 2. So what formula links them together? So V squared equals to U squared plus 2AS. So V being 9 root 2. So 9 root 2 squared equals to 15 squared plus 2 times minus 9.8 times by H, or yeah, because it's above, yeah, it will be positive H. So H therefore would be 15 squared minus 9 root 2 squared over 2 times by 9.8, 45 over 14. All right, quickly, part B, find the minimum speed of the ball as it moves from O to A. Where on the path will the minimum speed occur? Good, at the maximum, at the highest point. Because horizontally the speed doesn't change. It's gonna be 9 meters per second horizontally. Vertically, right, it starts off at 12 and then goes to 0 at the end, at the maximum height. And the speed is Pythagoras. Speed along the x squared plus speed along the y squared. So because we're adding up the components, and if you add nothing on the vertical one, that happens at the highest point. So therefore, minimum speed occurs at maximum height where velocity along the y would be 0. So therefore, at v would be equal to 9 squared plus 0 squared square root, which is 9, would be the minimum speed. Question C. Find length of time for which speed of the ball is less than 4 meters per second. Okay, so v. Well, we know that vx doesn't change. Vx is going to be always 9. So it's the vy that's the one that's going to change. So you want the speed of 12 meters per second. So the speed or the velocity of a projectile at any point will be vx and Vy. So the speed, therefore, which is the modulus, would be Vx squared plus the vertical speed, and then it would be the square root of that. This has to equal to 12 meters per second. And Vx, which doesn't change, is always 9 in this scenario. So 9 squared plus Vy squared equals to 12 squared, which is 144. So Vy squared, therefore, would be 144 minus 9 squared equals 63. So V, therefore, be plus or minus root of 63. So that tells us that if you draw a sketch, our object that does this, so it goes down like this, on its way up, the velocity of y would be positive root 63, and on its way down, the velocity in the y direction would be negative root 63. And we are asked to work out the length of time in which it stays above that or below that. Speed is less than 12 meters per second. So along this path of the motion, right? So at this point, the vertical speed is root 63. At the highest point is 0, so it reduces to 0 and then increases back to root 63 on its way down. In that region here, the speed is less than 12 meters per second. So v being equal to u plus at. So on its way up, v would be positive root 63. The initial vertical speed is 12. Because the initial vertical speed is equal to 12. So it would be 12 plus 9.8 times t. So this means 9.8 t would be equal to 12 minus root 63, and then t would divide that back to 9. So 12 minus root 63 divided by 9.8, that's 0.414565. And then on its way down, the vertical speed would be negative root 63 equals to 12 minus 9.8 times t. So that gives us 9.8 t equals to 12 plus root 63. So t therefore would be 12 plus root 63 divided by 9.8. That's 2.03441 . So if we call this t1 and call this t2, so at this time it's t1 and at this point it's t2. So the length of time the speed is less than 12 meters per second, therefore would be t2 minus t1. Subtract off 0.414565. Give it to 3SF, it's 1.6198, so approximately 1.62 seconds. All right, question. The model could be refined by considering air resistance. So just one other refinement to the model that will make it more realistic. For this part, you can just mention about the assumptions that were already stated in the question, but just say the alternative. So right, so if it's not moving freely under gravity, we could have the effect of wind. The ball could be spinning. The dimensions of the ball could affect. If the ball has dimensions, it will have a surface area. So again, spin could affect its motion. So it won't move in the same vertical plane. So yeah, so for part D, you can mention dimension of the ball. You can mention the effect of wind. You can also talk about the accuracy of G. G could be more accurate. So you can say any of those points just for that one mark. So question 5, we've got two packages, A and B, connected to each other on a pulley system. Mass of each one is 3 kilograms. A is initially held at rest on a smooth fixed plane, so we can ignore friction, inclined at theta degrees, where sine theta is 2 out of 7. The rope passes over pulley P fixed at the top of the plane. Pulley is modeled as small and smooth. The part of the string from A to P is parallel to the greatest slope, which just means it's on the inclined plane. and package B hangs freely below P. Packages are released from rest with the string toward, and A moves up the plane. So I'm going to write that in. So the motion of A is up the plane, is going to accelerate up the plane. At the same time, B will move down with acceleration A. It's a connected system, so the acceleration of both objects would be the same in terms of magnitude. The packages are modeled as particles, and the rope is light and inextensible string. The magnitude of tension in the rope or in the string immediately after packages are released is T. So we're going to have tension T pulling A up, and we're going to have tension T pulling upwards there. So let's start annotating the diagram with all the forces apart from, T is already there in the diagram. We're going to have the weight of particle or object A would be 3g acting vertically downwards, and the weight of B is also 3g. We will have a reaction force acting perpendicular to the slope. Let's call that reaction here, which is perpendicular to the inclined plane. Okay, so that's the forces annotated on the diagram. I haven't annotated the forces acting on the pulley, so if we need that, we can do that later on. Right now, all the forces acting on A and B are on the diagram. Just going to highlight the fact that the plane is a smooth plane, so we can ignore friction. Right, so next thing I'm going to do is I'm going to break up the forces acting at A into its component. The reaction at A is perpendicular to the plane, so that's fine. But the weight of our package A has to be broken up into its components, which are parallel and perpendicular to the plane. So that's the perpendicular component. This angle would be the same as theta. So the adjacent here would be 3g cos theta, and the opposite would be 3g sine theta. Now, given that sine theta is is 2/7, so if we draw a triangle, theta sine is opposite over hypotenuse. What's 49 minus 4 is 45, and root 45 is 3 root 5. So that's 3 root 5, which means cos theta would be adjacent over hypotenuse, so that's 3 root 5/7. Okay, so find the tension. To find the tension, we need to work out what the acceleration is, and then we can find tension. So we've got two objects moving in. Well, they're not moving in the same direction, so we can't model them as moving together. We can't do an equation of motion where they move together, so we have to do them separately. Okay, so let's start with package B. So for package B, F equals to ma. Now, because package B is moving downwards, the force acting downwards is 3g minus the opposing force, which is tension T, equals to its mass, which is 3 times the acceleration. There we go. So that's the equation of motion of particle or package B. Now, for package A, we're going to do F equals ma with that too. Package A is moving up the plane. We got tension, which is pulling it up the plane, minus the opposing force. Comes from gravity. That's 3g sine theta equals to its mass times the same acceleration. Now, sine theta is 2/7, so t minus 3g times by 2/7 equals to 3a. And I'm just going to multiply. No, I'll just keep it as it is actually. So t minus 6/7g equals to 3a. So that's our second equation. That's the first equation. Now, to work out what the tension is, first we're going to work out the acceleration by adding those two equations together. So if we do equation 1 plus equation 2, we can see that the minus t and the plus t will cancel off. So we're just going to have 3g minus 6/7g equals to 3a plus 3a. And if we simplify that, so 3 minus 6 over 7. So that's 15 over 7g equals to 6a. So therefore, acceleration would be 5 over 14. 14g is our acceleration. We just have to substitute this back into either equation 1 or 2. I'm going to substitute it back into equation 1. So 3g minus the tension equals to 3 times the acceleration. That's 15 over 14g. So if we rearrange and make t the subject, so that's 3g minus 15 over 14g. So 3 minus 15 over 14 gives you 27 over 14g, and then if we look at the magnitude, gives you 18.9 newtons. Okay, so that's the tension worked out. At the instant when the packages are released from rest, B is 0.8 meters above the ground, as we can see from the diagram, and A is at the point C on the plane. So when B is immediately brought to rest by the impact with the ground, in this subsequent motion, A does not reach the pulley and comes to instantaneous rest at point D on the plane. Find the distance from C to D. Let me draw another diagram for this one. This is question B. When the particle, when they're released, B is 0.8 meters above the ground, and A is at point C. And when B reaches the ground, B comes to rest, whereas A comes to point D on the plane. So A does not reach the pulley, and it comes to rest at point D on the plane. So particle A starts here. So here, particle A is at rest because it starts at rest. I'm gonna put B here, and I'm gonna put C there. So at C, we know that V equals to 0. At C is our particle. Our package A comes to rest at point C, but at point B, there's a velocity we need to work out. So at point B is where the package B hits the ground. So this is a point where package B hits the ground. Now, there's 2 stages to the motion of package A, from going from A to C. So during its motion from A to B, this is where both packages are connected. So when they're connected, they have an acceleration of A, which we worked out to be, was our acceleration? 5 over 14g. So from A to B, the acceleration is 5 over 14b. But the moment B hits the ground, the tension comes to 0. There's no more tension anymore. So when we look at the motion now from going from B to C, there's no more tension anymore. So the only thing acting on the object now to slow it down would be our 3g sine theta component of the force. So we're going to have to recalculate. We're going to have to calculate what the acceleration is for this phase, right? Even though tension is 0, that doesn't mean acceleration would be 0, because there is still a force acting on the package A as it moves from B to C. We're going to have to recalculate what that new acceleration is from B to C. So from B to C, if we have our package, let's say that's package A, from B to C, so let's say that's point B here, and it goes up to point C here. There's no more friction anymore. There's no friction anyway. There's no more tension anymore. So the only force acting on our package here would be due to gravity. So if we break up the component, I mean, it's the same annotation we already have in the previous diagram. It's this component of the force, which is 3g sine theta, is the only force that's acting parallel to the plane and slowing it down. So the resultant force, F equals ma. The resultant force acting, well, our object is moving up the plane, but there's no tension. Tension is now 0. So 0 minus the force down the plane is 3g sine theta equals to mass times acceleration, so equals to 3/8. And sine theta was 2 out of 7, was it? Yeah, 2 out of 7. So this would be minus 6 over 7 g equals to 3/8. So the new acceleration, therefore, is minus 2 over 7g. So here, I can place the new acceleration here. So this would be minus 2 over 7g from B to C. All right, so we need to work out, what we're asking to work out, find the distance from C to D. All right, to work out the distance from C to D, we need to work out the speeds of the package between C and D. Well, at C, we know that it's equal to 0, so that it comes to rest. We need to work out the speed that the package A acquires as it moves from A to B. So the speed at B would be the speed that B hits the ground with. That's the same speed that A acquires during that motion. So we know that it starts off at rest, is accelerating as 5 over 14g, and it reaches a speed of v, which we need to work out. Now the distance traveled from A to B is the same distance that B travels as it hits the ground, and that's equal to 0.8. So that distance here between A and B, the distance from A to B, so this distance is equal to 0.8 meters. So if we just apply that to Suvat, so S equals to 0.8, U equals to 0, V is what we want to work out, A is equal to 5 over 14g. So all that can go into V squared equals to U squared plus 2as. So V squared will be equal to 0 squared plus 2 times by 5 over 14 times by g times by s, which is 0.8, and then square root the answer. So this is equal to 28 over 5. Root that, I get 2 root 35 over 5 as our speed v. So if we go back to our diagram, the speed here is therefore 2 root 35 over 5. So this was going from A to B. Now for the motion from B to C, if we now do Suvat again, S is the distance we want to work out. That's the distance from B to C. U is now our 2 root 35 over 5. V is 0. A is what we worked out as minus 2 over 7g. And if we sub this into v squared again, v squared equals to u squared plus 2as. V squared is 0. U squared is going to be 28 over 5. Let me just write this down below. So 0 equals to 28 over 5 plus 2 times minus 2 over 7g times s, which is the distance BC we want to work out. So 4 over 7g times BC equals to 28 over 5. So BC therefore would be 28 over 5 times by 7 over 4g. Calculate what BC is. BC equals to 1. There we go. Right, so just realize I haven't annotated the points correctly on my diagram. So if we link it to the question itself, point C is actually point D, and point C is point A. So we are required to work out the distance from C to D. So therefore, C to D would be from C would be equal to 0.8 plus the distance from B to C or B to D in this case is 1 meters. So the final answer is 1.8 meters from from C to D. And the limitation, state two limitations of the model that could affect the reliability of the answers that we got. I mean, anything from saying that so the pulley itself may not be small or it may not be smooth. The string may not be, the rope may not be light, or it may not be an extensible string. If a string, if it is extensible, so you can stretch, then the tension again won't be constant. So acceleration won't be constant, and so on.